Data are either categorical or quantitative. Categorical data are often referred to as qualitative data because the data can be grouped in categories. Each element has an attribute or quality. Categorical data has either nominal or ordinal scale and can be either numeric or non-numeric. Statistical analyses are limited to frequency tables, bar charts, and pie charts. A frequency distribution is a tabular summary of data showing the frequency or number of items in each of several non-overlapping classes. The objective is to provide insights about the data that cannot be quickly obtained by looking only at the original data. The Murata-In example here shows the results of a sample of 20 guest responses to the hotel's customer survey. The survey asked customers to rate Murata's quality as being excellent, above average, average, below average, or poor. Three customers surveyed said Murata's quality was below average. 9 customers surveyed said Murata's quality was above average. 5 customers surveyed said Murata's quality was average. 2 customers surveyed said Murata's quality was poor. 1 customer said Murata's quality was excellent. The numbers in non-overlapping classes, excellent, above average, average, below average, or poor, are called frequencies. The frequencies of customers saying Murata's quality was poor is 2. The frequency of customers saying Murata's quality was below average is 3. The frequency of customers saying Murata's quality was average is 5. The frequency of customers saying Murata's quality was above average is 9. The frequency of customers saying Murata's quality was excellent is 1. Frequencies add up to the number of customers in a sample, which is 20. The relative frequency of a class is the fraction or proportion of the total number of data items belonging to the class. Since 2 people rated Murata's quality as poor, the relative frequency of customers saying Murata's quality was poor is found by dividing 2 by 20. The relative frequency of customers saying Murata's quality is poor is 0.1. Since 3 people rated Murata's quality as being below average, the relative frequency of customers saying Murata's quality was below average is found by dividing 3 by 20. The relative frequency of customers saying Murata's quality was below average is 0.15. Since 5 people rated Murata's quality as average, the relative frequency of customers saying Murata's quality was average is found by dividing 5 by 20. The relative frequency of customers saying Murata's quality was average is 0.25. Since 9 people rated Murata's quality as above average, the relative frequency of customers saying Murata's quality was above average is found by dividing 9 by 20. The relative frequency of customers saying Murata's quality was above average is 0.45. Since 1 person rated Murata's quality as excellent, the relative frequency of customers saying Murata's quality was excellent is found by dividing 1 by 20. The relative frequency of customers saying Murata's quality was excellent is 0.05. The relative frequency distribution is a tabular summary of a set of data showing the relative frequency for each class. The sum of relative frequencies equals 1. Percent frequencies are found by multiplying relative frequencies by 100, and they sum up to 100. Bar charts can use frequencies, relative frequencies, or percent frequencies. Since the y-axis on the one labeled below is labeled frequency, we want to construct a bar graph for the frequency of a customer ratings at Murata-In. Since the frequency of customers saying Murata's quality was poor is equal to 2, the bar for this category stops at 2. Since the frequency of customers saying Murata quality was below average is 3, the bar for this category stops at 3. Since the frequency of customers saying Murata's quality was average is 5, the bar for this category stops at 5. Since the frequency of customers saying Murata's quality was above average is 9, the bar for this category stops at 9. Because the frequency of customers saying Murata's quality was excellent is equal to 1, the bar for this category stops at 1. Notice there are gaps in between the bars. This is not the case when the variable has interval or ratio scale. The pie chart is commonly used as a graphical device for presenting relative or percent frequency distributions for qualitative data. You begin by first drawing a circle. The relative frequencies are used to divide the circle into sectors that correspond to the relative frequency for each class. The above average class has a relative frequency of 0.45, so it consumes nearly half of the circle. The average class has a relative frequency of 0.25, so it consumes a quarter of the circle. The below average class has a relative frequency of 0.15, so it consumes less than a quarter of the circle. The poor class has a relative frequency of 0.1, so its slice of the pie is slightly less than the slice corresponding to below average class. The excellent class has a relative frequency of 0.05, so it consumes the remaining part of the circle that should be smaller than the slice corresponding to poor class. The pie chart imparts information in an efficient and compact manner. Insights gained from Murata and pie chart includes one half of customers surveyed gave Murata a quality rating of above average or excellent. Now this should please the manager. On the other hand, for each customer who gave the hotel an excellent rating, there were 2 customers who gave the hotel a poor rating. This should not be well received by the manager. Recall from Chapter 1 that quantitative data uses numeric values to indicate how much or how many. Quantitative data can be discrete or continuous. The number of cans of Coca-Cola sold by the gas station near your house is an example of a discrete variable. The volume of gasoline sold by the same gas station is an example of a continuous variable. Quantitative data is always numeric, and so arithmetic operations, multiplication, addition, subtraction, are meaningful. Statistical analyses not only include frequency tables, bar charts, and pie charts, but also averages, standard deviations, and correlations. In Chapter 1, we constructed a histogram and computed the sample mean for the Hudson Auto Repair example. If you recall, the manager of the garage wanted to compile statistical summaries of several variables associated with the operation of her garage. One of the variables of interest is the cost of parts used in tune-ups. She randomly selected 50 tune-up invoices. She entered the cost of parts, rounded to the nearest integer, into an Excel spreadsheet, like the data shown below. Sorting the data from the minimum value of 52 to the maximum value of 109 is helpful in understanding how medians, modes, and percentiles are found. In the previous chapter, we chose intervals with a width of 10. Well, how do we come up with this? First, you decide how many classes you need, and then determine the class width. Typically, you want between 5 and 20 classes. Classes are sometimes referred to as intervals. Excel refers to them as bins and categories. The larger your data set, the more classes you generally need. For smaller data sets of, say, size 25 to 30, you use 5 classes. The goal of choosing the number of classes is to get a good idea of what the distribution might look like. Next, you must decide how wide each interval should be. The following guidelines for selecting class width represent a rule of thumb. Pick 9 numbers nice numbers like 5, 10, 25, 50, 100, etc. First and foremost, use class widths of equal width. The approximate class width is found by subtracting the minimum from the maximum value and then dividing this difference by the number of classes you want. We chose 6 classes in the previous video for our Hudson auto repair data, whose minimum and maximum values were 52 and 109. So the class width according to this equation is 9.5. Well, this isn't a nice number. We chose instead the number 10 because it is nice. So 10 was our class width. Since the smallest value is near the nice number of 50, and our class width is 10, our first interval is 50 to 59. Although the difference of the two numbers is 9, there are 10 numbers from 50 to 59. Because this data is discrete, remember, the owner of the repair shop rounded the dollar values to the nearest dollar. The first interval, 50 to 59, contains 2 invoices. Hence, the frequency or count in this interval is 2. The second interval, 60 to 69, contains 13 invoices. Hence, the frequency of this interval is 13. The third interval, 70 to 79, contains 16 invoices. Hence, the frequency of this interval is 16. The fourth interval, 80 to 89, contains 7 invoices. The frequency of this interval is 7. The fifth interval, 90 to 99, contains 7 invoices. The frequency of this interval is 7. The sixth and final interval, 100 to 109, contains 5 invoices. The frequency of this interval is 5. Notice that the minimum of 52 and the maximum, they're in their respective intervals. The frequencies in the intervals 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99, and 100 to 109 are 2, 13, 16, 7, 7, and 5. These sum to the sample size of 50. The relative frequency of a class is the fraction or proportion of the total number of data items belonging to the class, in this case, interval. Since the frequency of invoice between 50 and 59 is 2, the relative frequency of this interval is found by dividing 2 by 50. The relative frequency of this interval is 0.04. 2 divided by 50 is 0.04. Since the frequency of the invoice between 60 and 69 is 13, the relative frequency is found by dividing 13 by 50. So the relative frequency is 0.26. The frequency of invoice between 70 and 79 is 16. The relative frequency of this interval is found by dividing 16 by 50, which is 0.32. The frequency of invoice between 80 and 89 is 7. The relative frequency of this interval is found by dividing 7 by 50, or 0.14. The frequency of invoice between 90 and 99 is 7. The relative frequency of this interval is found by dividing 7 by 50, which is 0.14. The frequency of invoice between 100 and 109 is 5. The relative frequency of this interval is found by dividing 5 by 50. So the relative frequency of the last interval is 0.1. The sum of relative frequencies is always 1. The sum of frequencies is always n, in this case 50. The percent frequency of interval 50 to 59 is found by multiplying the relative frequency, 0.04, by 100, which is 4%. The percent frequency of interval 60 to 69 is 26%. The percent frequency of interval 70 to 79 is 32%. The percent frequency of interval 80 to 89 is 14%. The percent frequency of interval 90 to 99 is 14%. The percent frequency of interval 100 to 109 is 10%. the sum of percent frequencies always equals 100%. Histogram is a bar graph, but a bar graph is not necessarily a histogram. The bars of a histogram have no gaps between them, and their widths are equal to the width of the intervals used in the frequency table. If percent frequencies are used, the histogram is a percent frequency histogram. In this diagram below, the y-axis says frequency. So we're going to construct a frequency histogram. Since the frequency of interval 50 to 59 is 2, the bar corresponding to this interval stops at 2. Since the frequency of interval 60 to 69 is 13, the bar corresponding to this interval stops at 13. Since the frequency of interval 70 to 79 is 16, the bar corresponding to this interval stops at 16. The frequency of interval 80 to 89 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 90 to 99 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 100 to 109 is 5. The bar corresponding to this interval stops at 5. The area, the total area of the red bars is 50. If this were a percent frequency histogram, the red bars would have an area equal to 100%. If this were a relative frequency histogram, the red bars would have an area equal to 1. Now the histogram estimates the true distribution of tune-up parts cost. In most cases, we won't know the true distribution of this variable. The area under the true distribution is equal to 1. For the same reason, the bars of a relative frequency histogram have an area equal to 1. The histogram suggests the data is positively skewed, or skewed right, since the right tail, the bars corresponding to intervals 80 to 110, is longer than the left one, the bar corresponding to interval 50 to 59. A histogram graph using data from a sample drawn from a symmetric distribution, heights and weights of people, will be symmetric with a skew equal to 0. Note, the mean and skew are sample statistics if computed from sample data. When skew equals 0, the left tail is a mirror image of the right tail. A histogram graph using data from a sample drawn from a distribution that is moderately skewed left will have a tail, left tail, that is slightly longer than its right tail. When the left tail is slightly longer than the right one, the skew is close to 0, but negative. A histogram graph using data from a sample drawn from a distribution that is moderately skewed right will have a right tail slightly longer than its left one. When the right tail is slightly longer than the left one, the skew is close to 0, but positive. A histogram graph using data from a sample drawn from a distribution that is heavily skewed right will have a right tail much longer than its left one. When the right tail is much longer than the left one, the skew is positive and large. The cumulative frequency distribution shows a number of items with values less than or equal to the upper limit of each class. The cumulative frequency of interval 50 to 59 is the frequency of invoices with parts costing at most $59, which equals 2. The cumulative frequency of interval 60 to 69 is the frequency of invoices with parts costing at most $69. Since there are 2 invoices between 50 and 59 and 13 invoices between 60 and 69, the cumulative frequency is 15. The cumulative frequency of interval 70 to 79 is the frequency of invoices with parts costing at most $79. Since there are 2 invoices between 50 and 59, 13 invoices between 60 and 69, and 16 between 70 and 79, the cumulative frequency of this interval is 31. The cumulative frequency of interval 80 to 89 is the frequency of invoices with parts costing at most $89. Since there are 2 between 50 and 59, 13 between 60 and 69, 16 between 70 and 79, and 7 between 80 and 89, the cumulative frequency of this interval is 38. The cumulative frequency of interval 90-99 is the frequency of invoices with parts costing at most $99. There are 2 between 50 and 59, 13 between 60 and 69, 16 between 70 and 79, 7 between 80 and 89, and 7 between 90 and 99. The cumulative frequency of this interval is 45. The cumulative frequency of the final interval is always equal to the sample size, which is 50. The cumulative relative frequency distribution shows a proportion of items with values less than or equal to the upper limit of each class. All the cumulative relative frequencies are between 0 and 1. Since the cumulative relative frequency of invoices with parts costing at most $59 is 2, the cumulative relative frequency of this interval is found by dividing 2 by 50, which is 0.04. The cumulative frequency of invoices with parts costing at most $69 is 15. The cumulative relative frequency of this interval is found by dividing 15 by 50, which is 0.30. The cumulative frequency of invoices with parts costing at most $79 is 31. The cumulative relative frequency of this interval is found by dividing 31 by 50, which is 62, or 0.62. Since the cumulative relative frequency of invoices with parts costing at most $89 is 38, the cumulative relative frequency of this interval is found by dividing 38 by 50, which is 0.76. The cumulative frequency of invoices with parts costing at most $99 is 45. The cumulative relative frequency of this interval is found by dividing 45 by 50, which is 0.90. Since the cumulative frequency of invoices with parts costing at most $109 is 50, the cumulative relative frequency of this interval is found by dividing 50 by 50, which is 1. The cumulative relative frequency of this interval is 1 and is always 1 because it is the final interval. And the final interval of any cumulative relative frequency is always equal to 1. The cumulative percent frequency distribution shows a percentage of items with values less than or equal to the upper limit of each class. Multiplying all the cumulative relative frequencies by 100 yields cumulative percent frequencies. The cumulative percent frequencies are 4, 30, 62, 76, 90, and 100. The final cumulative percent frequency is always equal to 100%. An ogive is a graph of a cumulative distribution. On the y-axis, we could have cumulative percent frequency, or cumulative relative frequency. In the diagram here, the y-axis is labeled cumulative percent frequencies. Hence, this ogive is a cumulative percent frequency distribution. The percent of invoices with parts costing at most $59 is 4%. Now, this is the same as saying the percent of invoices with parts costing less than 60 is 4%. Hence the height of 4% at the value 60. We can also say that the percent of invoices with parts costing less than $50 is 0%. So this ogive starts at $50 and 0%. Then travels to the point $60 and 4%. The ogive next travels to point $70 and 30%. Because the percent of invoices with parts costing at most 69 or less than 70 is 30%. Next, we go to point 62. Because the percent of invoices with parts costing at most $79 or less than 80 is 62%. Next we go to point 90 and 76. Because the percent of invoices with parts costing at most $89 or less than $90 is 62%. The percent of invoices with parts costing at most $99 or less than $100 is 90%. The percent of invoices with parts costing at most $109 or less than $110 is 100%. All cumulative percent frequency ogives end at 100%. All cumulative relative frequency ogives end at 1. Thus far, we've focused on methods that are used to summarize the data for one variable at a time. However, many variables are related. For example, the local football team. If it wins more games, more people show up at home games. More people at home games means higher hot dog sales. Often a manager is interested in tabular and graphical methods that will help understand the relationship between two variables. These methods can improve the quality of their decisions. If the football team is having a bad season, attendance will be lower than in previous years. If the manager of the concession stand does not understand this, he or she might order too many hot dogs. A cross-tabulation table and a scatter diagram are two methods for summarizing the data for two variables simultaneously. Cross-tabulation tables, called pivot tables in Excel, can be used to show the presence of a relationship between two variables. Now, just because a cross-tabulation shows the presence of a relationship between two variables doesn't necessarily mean there is causation between one to the other, or vice versa. Cross-tabulation can be used when one variable is qualitative and the other is quantitative, or both variables are qualitative, or when both variables are quantitative. If both variables are quantitative, the variable can be also summarized by a scatter plot. The left and top margin labels define the classes for the two variables. The cross-tabulation is essentially three frequency tables in one. The data for this example is contained in an Excel file called fingerlakeshomes.xls. There are two variables in this data set. One of them is a quantitative variable called price range. According to the cross-tabulation table, the intervals we chose are homes costing at most $99,000 and those costing more than $99,000. The other variable is qualitative. Homes sold in Finger Lakes are either colonial, log, split, or A-frame. There are 18 homes that are of colonial style and less than or equal to $99,000. 6 are log and priced at $99,000 or less. 19 are split and priced at $99,000 or less. 12 are A-frame and priced at $99,000 or less. 12 are colonial and priced at more than $99,000. 14 are log and priced at more than $99,000. 16 are split and priced at more than $99,000. And 3 are A-frame and priced at more than $99,000. 55 are priced at $99,000 or less. 45 are priced at more than $99,000. 30 are colonial, 20 are log, 35 are split, and 15 are A-frame. There are a total of 100 homes in this data. The greatest number of homes in the sample, 19, are split level and priced at less than or equal to $99,000. Only 3 homes in the sample are A-frame and priced at $99,000 or more. The leftmost and rightmost columns comprise a frequency distribution for the price range of homes. The frequency in this table sums the size of the sample, which is 100 homes. The top and bottom rows comprise frequency distribution for home style. The frequencies in this table sum the size of the sample, which is 100 homes. The table inside the margin comprises a frequency distribution for joint events. A joint event is, for example, the event that a home is colonial and has a price that is less than or equal to $99,000. The sum of these frequencies in this yellow box add up to 100. Converting the entries in a cross-tabulation table into row percentages or column percentages provides additional insight about the relationship between the two variables. Row percentages and column percentages will be referred to as conditional probabilities in future videos. In this example, row percentages are probabilities conditional on home price. To compute row percentages, ignore the column totals. The row percentage in the first row and first column is found by dividing 18 by 55. The resulting value can be interpreted as a probability of a randomly chosen home being colonial given it is priced at $99,000 or less, which is equal to 0.3273 or 32.73%. The next row percentage in the top row is found by dividing 6 by 55. The resulting value can be interpreted as a probability of a randomly chosen home being a log given it is priced at $99,000 or less, which is equal to 0.1091 or 10.91%. The next row percentage in the top row is found by dividing 19 by 55. The resulting value can be interpreted as the probability of a randomly chosen value being split given it is priced at $99,000 or less, which is equal to 0.3455 or 34.55. The last row percentage in the top row is found by dividing 12 by 55. The resulting value can be interpreted as a probability of a randomly chosen home being A-frame given its price is $99,000 or less, which is equal to 0.2182 or 21.82%. The top row of the row percentages table is a frequency distribution. Hence, the sum of these percent frequencies is 100%. The row percentages in the second row and first column is found by dividing 12 by 45. 45. The resulting value can be interpreted as a probability of a randomly chosen home being colonial given its price is more than $99,000. It is equal to 0.2667 or 26.67%. The next row percentages is found by dividing 14 by 45. The resulting value can be interpreted as the probability of a randomly chosen home being log given it is priced at more than $99,000. It is equal to 0.3111 or 31.11%. The next row percentage is found by taking 16 and dividing it by 45. It can be interpreted as the value or the probability of a randomly chosen home being split given is priced at more than $99,000. It is equal to 35.56%. The next row percentage in this row is found by dividing 3 by 45. It can be interpreted as a probability of a randomly chosen home being A-frame given it is priced at more than $99,000. It is equal to 6.67%. The bottom row of percentages is a frequency distribution itself, and the sum of these values is 100%. In our example, we can compute column percentages as probabilities conditional on home style. We're going to ignore the row totals. The column percentage in the first row and first column is found by dividing 18 by 30. The resulting value can be interpreted as a probability of a randomly chosen home being priced at $99,000 or less given it is colonial, which is equal to 60%. The next column percentage in the first column is found by dividing 12 by 30. The resulting value can be interpreted as the probability of a randomly chosen home being priced at more than $99,000 given its colonial, which is equal to 40%. The first column of column percentages is a frequency distribution, and their sum is 100. The column percentage in the first row and second column is found by dividing 6 by 20. The resulting value can be interpreted as the probability of a randomly chosen home being priced at $99,000 or less given it is log, which is equal to 30%. The next column percentage in the second column is found by dividing 14 by 20. The resulting value can be interpreted as a probability of a randomly chosen home being priced at more than $99,000 given it as log, which is equal to 70%. The second column of column percentages is a frequency distribution. Hence, the sum of these frequencies, percent frequencies, is 100%. The column percentage in the first row and third column is found by dividing 19 by 35. This can be interpreted as a probability of a randomly chosen home being priced at $99,000 or less given its split, which is equal to 54.29%. The next column percentage in the third column is found by dividing 16 by 35. It can be interpreted as a probability of a randomly chosen home being priced at more than $99,000 given its split, which is 45.71%. This third column of percentages is a frequency distribution, and its sum is 100%. The column percentage in the first row and fourth column is found by dividing 12 by 15. The resulting value can be interpreted as a probability of a randomly chosen home being priced at $99,000 or less given its A-frame, which is equal to 80%. The next column percentage in the fourth column is found by dividing 3 by 15. The resulting value can be interpreted as the probability of a randomly chosen home being priced at more than $99,000 given it is A-frame. It is equal to 20%. The fourth column of column percentages is a frequency distribution. Hence, the sum of these percent frequencies is 100%. A cross tabulation can be misleading if the data is aggregated. An aggregated cross tabulation is one that results when two cross tabulations are combined. The aggregated cross tabulation can, in some instances, provide a decision maker with a flawed conclusion. One must be very careful when drawing conclusions about the relationship between two variables in an aggregated cross tabulation because of a phenomenon called Simpson's paradox. Simpson's paradox is a situation in which the conclusions based upon aggregated cross tabulation can be completely reversed if we look at unaggregated data. A famous Simpson's paradox looked at death penalty rates of black and white convicted murderers, which found that whites had a slightly higher death penalty rate when an aggregated cross tabulation is used. However, when cross tabulations are disaggregated by race and of the victim and the convict, black convicts had higher death penalty rates in both cases. Another famous Simpson's paradox involves the University of California at Berkeley. In 1973, there were 12,763 applicants for graduate admission. 8,442 were male, and 4,321 were female. That year, 3,738 and 1,494 males and females were admitted, respectively. Building an aggregated cross tabulation is straightforward. The frequencies from the previous slide have already been entered in this table below. 8,442 males, 4,321 females, 12,763 total applications to graduate programs at UC Berkeley, 3,738 males admitted, 1,494 females admitted. To complete this table, add the two frequencies in the admitted column. The sum of these frequencies says that 5,232 students were admitted to UC Berkeley's graduate school. Next, in the male row, subtract the frequency of male applicants accepted, 3,738, from the frequency of male applicants, 8,442. Hence, the frequency of male applicants denied was 4,704. Do the same thing with females. And then add these two values together to get the total denied. 7,531 students were not admitted to UC Berkeley's graduate school program. Dividing all the frequencies in aggregated cross tabulation generates what we will call the joint probability table in Chapter 4. Male and female acceptance rates will appear in the first two rows of the first column of this table here. The relative frequency of male applicants, this value here, is computed by dividing the frequency of male applicants, 8,442, by the frequency of applicants, 12,763. Hence, the relative frequency of male applicants is 0.6614. The relative frequency of female applicants is computed by dividing the frequency of female applicants, 4,321, by the frequency of applicants, 12,763. Hence, the relative frequency of female applicants is 0.3386. These sum to 1. The relative frequency of male applicants denied admission is computed by dividing the frequency of males denied by the frequency of applicants, 12,763. Hence, the relative frequency of male applicants denied admission was 0.3686. The relative frequency of female applicants denied admission is computed by dividing the frequency of females denied, 2,827, by the frequency of applicants, 12,763. Hence, the relative frequency of female applicants denied admission was 0.2215. The relative frequency of denying applicants admission is computed by dividing the frequency of students denied, or applicants denied, 7,531, by the total number of applicants, 12,763, which equals 0.5901. Now, this 0.5901 is also found by adding these two relative frequencies. This value here is going to be called the marginal probability in Chapter 4. These two values here are called joint probabilities in Chapter 4. The male acceptance rate cited by the female applicant alleging UC Berkeley's admission policies to discriminate against women was computed by dividing the frequency of males admitted, 3,738, by the frequency of applicants, 12,763. Hence, the male acceptance rate in 1973 at UC Berkeley was 0.2929. The female acceptance rate is computed by dividing the frequency of females admitted, 1,494, by the frequency of applicants, 12,763. The female acceptance rate was 0.1171 in 1973 at UC Berkeley, which is much lower than the male acceptance rate. To get the acceptance rate overall, one takes the number that are admitted divided by the total number of applicants, which in this case equals 0.4099. Now, again, this is a marginal probability of being admitted. These two here are joint probabilities. This is the probability that a male is admitted, this is the probability that a UC Berkeley Graduate School applicant is male and admitted. This is the probability that a UC Berkeley Graduate School applicant is female and admitted. Again, the male acceptance rate appears to be higher when the data is aggregated. The lawyers representing the University of California, Berkeley used data disaggregated to the department level. This is the appropriate way of summarizing data because admission decisions are made at the department level. In 1973, the university had 101 different graduate departments. We are only going to look at the top two departments, which we call departments A and B. The disaggregated admissions data is given in the tables below. Computing row percentages, which are referred to as conditional probabilities in Chapter 4, reveals Simpson's paradox. The relative frequency of males admitted, given they applied to Department A's graduate program, is computed by dividing the frequency of males admitted to Department A's graduate program, 512, by the frequency of males that applied to Department A's graduate program, 825. The relative frequency of males admitted, given they applied to Department A's graduate program, is 0.6206. The relative frequency of males denied admission, given they applied to Department A's graduate program, is computed by dividing the frequency of males not admitted to Department A, 313, by the frequency of males that apply to Department A, 825, which is 0.3794. Both of these add up to 1. The relative frequencies admitted, given they apply to Department B's graduate school program, is computed by dividing the frequency of males admitted to Department B's program, 313, by the frequency of males that apply to Department B's graduate program, 520. The relative frequency of males admitted, given they applied to Department B's graduate program, is 0.6019. The relative frequency of males denied admissions, given they applied to Department B's graduate program, is computed by dividing the frequency of males not admitted to Department B's program, 207, by the frequency of males that applied to Department B's graduate program, 520. The relative frequency of males denied, given they applied to Department B's graduate program, was 0.3981. These two probabilities, or relative frequencies, again add up to 1. The relative frequency of females admitted, given they apply to Department A's graduate program, is computed by dividing the frequency of females admitted to Department A's graduate program, 89, by the frequency of females that apply to Department A's graduate program, 108. This relative frequency of females admitted, given they applied to Department A's graduate program, was 0.8241. The relative frequency of females denied admission, given they applied to Department A's graduate program, is computed by dividing the frequency of females not admitted to Department A's graduate program, 19, by the frequency of females that applied to Department A's graduate program, 108. The relative frequency of females denied, given they applied to Department A's graduate program, was 0.1759. These two probabilities, or relative frequencies, add up to 1. The relative frequency of females admitted, given they applied to Department B's graduate program, is computed by dividing the frequency of females admitted to Department B's graduate program, 17, by the frequency of females that applied to Department B's graduate program, 25. The relative frequency of females admitted, given they applied to Department B's graduate program, was 0.680. The relative frequency of females denied, given they applied to Department B's graduate program, is computed by dividing the frequency of females not admitted to the Department B's graduate program, 8, by the frequency of females that applied to Department B's graduate program, 25. The relative frequency of females denied admission, given they applied to Department B's graduate program, was 0.3200. And these two add up to 1 again. The female acceptance rates are higher in both departments. In actuality, they are higher in all 101 graduate programs. This is the Simpson's paradox. At the aggregated level, males have higher acceptance rates. By department, the acceptance rates are higher than their male counterparts. When two variables are quantitative, a cross-tabulation or scatter plot can be used to determine if they are related. A scatter diagram is a graphical presentation of the relationship between two quantitative variables. One variable is shown on the horizontal axis. The variable on the horizontal axis is generally called the independent variable. The dependent variable is typically on the vertical axis, unless you're in microeconomics. The pattern of the plotted points suggests the overall relationship between the two variables. The pattern can suggest a positive or negative relationship between the two variables, but can also suggest that there is no relationship between them as well. A line that best fits the data is called a regression line. Excel calls this a trend line. This line is an approximation of the relationship between the two variables. It can also be thought of as an expectation of what to expect given the value of x. The closer the points lie to the line, the stronger is the relationship between the variables. A negative relationship is probable if the points in a scatter plot are lower as the values of the variable on the horizontal axis increase. So when x is 0.50, y is 21. When x is 5, y is 2, Then you plot the other points in there. And this relationship, the relationship between y and x, does appear to be negative. If x is the price of Big Macs and y is the quantity demanded for Big Macs, then the red line represents the demand curve for Big Macs. A positive relationship is probable if the points in the scatter plot are higher in general as the values of the variable on the horizontal axis increase. A researcher plots 13 points. In total, these points suggest there's a positive relationship between y and x. Suppose x is the price of Big Macs. Y is the quantity demanded for Whoppers. The red line suggests that as the price of Big Macs increases, the quantity demanded for Whoppers increases. This makes sense because people will consume fewer and fewer Big Macs and more Whoppers as the price of Big Macs rise. This diagram suggests that Big Macs and Whoppers are substitutes. No relationship is probable if the height of the points in the scatter plot generally do not increase or decrease as the values of the variable on the horizontal increase. A researcher again plots 13 points. In total, these points suggest there is no relationship between y and x. Suppose x is the price of Big Macs and y is the quantity demanded for nose hairs trimmers. The red line suggests that as the price of Big Macs increases, the quantity demanded for nose hairs trimmers does not change. This diagram suggests that Big Macs and nose hair trimmers are neither substitutes nor complements. The example below will be used to generate a scatter plot of Panthers football team's interceptions and points scored. When the Panthers have one interception, they scored either 14 points as a team, or they scored 17 combined points as a team. When they made two interceptions, they scored 18 points as a team. When they had three interceptions, they scored 24 points as a team and 30 points as a team. In total, it seems that this data is suggesting that as interceptions increase, points scored increases. This is easier to see with a scatter plot. Plotting the points in the previous table generates a scatter plot with the number of points scored on the y-axis and the number of interceptions on the x-axis. In the first game, the Panthers had one interception and scored 14 points in total. In the second game, the Panthers had three interceptions and scored 24 points as a team. In the third game, the Panthers had two interceptions and scored 18 points. In the fourth game, the Panthers had one interception and scored 17 points as a team. In the fifth game, the Panthers had three interceptions and scored 30 points as a team. The scatter plot explicitly shows there seems to be a positive relationship between interceptions and points scored. The scatter plot helps us gain a deeper understanding of the relationship between interceptions and points scored. The diagram indicates a positive relationship exists between interceptions and points scored. The team scores more points as the number of interceptions rise. This relationship is, of course, not perfect because there's a lot of variables that go into points scored. Is the offense predominantly a rushing team? If they're predominantly a rushing team, they're going to score fewer points than a passing team. Does the defense give up a lot of yards? Does the defense give up a lot of points? If so, their offense is going to be on the field more, scoring more points. So it's not a perfect relationship, and there is information missing.